Hello everyone, welcome to the Material Science class, MIC 300. This is chapter 6. In this chapter we are going to discuss the mechanical properties of metals. So we are going to start with the simple tensile test. This tensile test, it is a mechanical method of determining some of the properties of this material, and these properties are commonly known as mechanical properties. But so we do have mechanical method of determining the mechanical properties. So why the focus is over these mechanical properties? Something that you should understand, that since these properties are mechanical, this doesn't mean that they are already of interest to mechanical engineer. No, these properties are in general are of interest to engineers. So here we are dealing with the material from the engineering perspective. As we said, there is a difference between material science and material engineering. So in this chapter, we're just gonna talk engineering. We're gonna focus more on the application side of these materials, and we're gonna deal with them like they are material engineering from the material engineering perspective. So to determine any material, as we discussed before, it has some chemical, physical, and mechanical properties. Some of these mechanical properties, for example, like the Young's modulus or elastic modulus of the material, the yield strength, the ductility. So all of these are properties which are qualified as mechanical properties. These properties are the properties that we depend on when we are dealing with this material as engineer. Whatever you are, civil engineer, mechanical engineer, chemical engineer, in the engineering perspective, these mechanical properties are important to know them in order to know how we can apply this material for different application or use this material for different application. One of the methods of determining these properties is the simple tensile test or the tensile test or the tension test. So all are the same titles or name of this experimental method of determining these properties. And this method, it is a mechanical approach. It is a mechanical method. Why it is mechanical method? Because we are using a machine. And any machine, it is something that is related to mechanical. So that's why we are giving name to the properties that would drive using the simple tensile test as mechanical properties. This indicates that these properties had been driven using a mechanical method or using a mechanical method of testing the material to determine these mechanical properties or determine these properties of the material. So the tension test is one of the most common mechanical material tests. This indicates there are lots of other methods by which we can determine mechanical and even physical and chemical properties of the material. But the simple tensile test, if we are interested in these mechanical properties, definitely the easiest way is to use this mechanical method, which is the simple tensile test. Make sense? The tension test can be used to estimate or determine several mechanical properties of the material, like, for example, as I mentioned, the Young's modulus, the yield strength, in addition to so many other mechanical properties that we're gonna go over them, and I'm going to show you how we can determine these mechanical properties using the tension test. These material properties are needed for the design or the implementation or the use of these materials in different mechanical applications, in different engineering applications in general, whatever, civil engineering, chemical engineering, even we could use them. We should have knowledge about these mechanical properties in order to manufacture the material. In terms of manufacturing or material making, we should have an idea about these mechanical properties. Also, from the engineering science perspective, we said that the engineering science, it is 4 disciplines. We do have material properties, so here we are talking about the properties and how we can determine them, and the focus is over these mechanical properties. Also, we do have material processing, how we can make a material making, this manufacturing of the material. We could use a chemical method, we could use a mechanical method. So for example, if you are going to make a material using a mechanical approach, definitely you should have an idea about this raw material that you are using for making material and what its mechanical properties in that case. Even for the other discipline of material science is material performance, or which is already covered in the mechanics of material class. Material performance, you should have an idea. It depends on the properties of the material itself, as we are going to explain. So generally, the tensile test is one of the mechanical methods which is very important to use them to determine these mechanical properties. And that's why this is the focus of this chapter in chapter 6. Alright, so during the tensile test, the material is subjected to a force. This force will be used to generate a tensile stress, and that's why this stress should be tensile. Tensile, it means that the tendency of this stress is to stretch the material, to achieve an elongation, an increase in the length of the material sample. That we prepare a material sample or a sample of the material that we would like to test, then we are going to stretch this material till the complete fraction. This is the basic, the simplest idea of the simple tensile test. So this stretch that the machine produces over the material, it can be converted or represented as a tensile stress. It requires a tensile stress, and this tensile stress, it can be produced because of a force, which is F, and this force can be related to sigma. So this sigma, this is the stress that I'm talking about. This is the tensile stress. It can be simply generated through a force. Like we can apply this stress through a force acting over the material sample, and if we divided this force over A, which stands for the cross-sectional area of the material sample, we can simply generate a stress that would be acting on the material to enforce the material to be stretched or to increase the length of the material sample. It works typically the same way, like if I give you a string and I ask you to stretch it. So simply you're just gonna start to move one hand and fix the other hand, or simply you can move both hands in the two opposite directions, so the string will be keep on stretching. So what you are doing now, you already applying a stress. You are applying a force. If you divided the force over the area, this is gonna generate another measure, which is known as the tensile stress, that is responsible for increasing the length of the string. Typically the same thing, this is what we are doing in the tensile test. Even if you're gonna keep on stretching the spring by hands in two opposite sides, at a certain instant of time, this string will be cut. This is typically what is going to happen into the material sample. So we are dealing with this material sample using the machine, whatever it is, made of any metal material, and we fixing this one over the machine, and the machine do the same thing that we used to do for the string. Till the material, it will be completely cut or completely fractured up on the stretch that is generated because of the increase in the tensile stress. So how the tensile stress during the simple tensile test is generated, this requires a force, and how it could be related to the force, it is equal to the force divided by the cross-sectional area of the material sample. This is a schematic that represents the shape of the simple tensile testing machine. It is a machine, so that's why it is a mechanical method. This is a simple diagram represent how the simple tensile test machine already composed of. Definitely there should be a bar screw that it rotates. Once it rotates, it's gonna give a movement to this moving head. So this is a head or a platform that is going to move, and this is the material sample that is screwed, that is fixed to these two heads. So this head is fixed. The other head of the machine is movable, moves down, and this, as this head moves down, this is gonna produce a stretch into this material sample. As I said, deal with it like it is made of plastic, like it is made of a rubber material, or it is a string. Although it is already metal material, which is very strong material, so that's why we are using machine to apply an enough amount of stress so we can able to stretch this material to be completely fractured. So, but it works in the same way, like we are fixing the head, one head, and moving the other one. The movement of the other one is going to generate because of this power screw, and the material, it is specially designed. This is a sample, not that represent the entire material type. Like for example, if you would like to test steel, so simply you're gonna prepare a material sample with this shape, and then you are going to test it. Any mechanical properties that you are going to derive from that test will be representative for all the kind of this material, for all steel with the same specifications. Make sense? So that's why it is named as a material sample, that we bring this sample, we prepare this sample, and we fix it over the machine, test the sample. Any property that we can drive here, it will be representative for all the kind of this material sample. Make sense? So we prepare this material sample. This is the standard form of the material sample, but in many of the cases, it is not necessary to stick to these properties or to this standard thing. We can do changes over the shape and the dimensions of this standard form or shape of the material sample. But this is based on if we are interested to stick to the standard method of tensile test, we have to prepare the material sample into this bone shape as already given, sticking to this dimension. Like for example, according to the standard, the diameter it should be 0.005 inches, and the bigger diameter of this bone shaped material sample it should be 3/4 inches, and the gauge length, this is the original length of the material sample, or the length of the material sample, which represent the exact length of the sample that we would like to test. This is gonna be 2 inches, and we're gonna have another reduced section length of 2/4 inches. In addition, we're gonna have this fillet that will be used to relieve the stresses or the stress concentration at this region. So basically, we could say that the exact material sample that we should be testing is this one. Starting from this line to this line, this is our material sample. But how about the other features? These other geometries, we are making them specially to allow for fixing this material sample into the machine. So basically, one of the things that we could generate some screws over this side and apply another screw or thread over the other side. Then we're gonna use these screws or threads to fix the material sample as shown here into the figure, into the machine. And we are using two main sensors. One sensor is already embedded inside the machine. This sensor is known as the force sensor, that is gonna measure how much of force that the machine is going to generate or apply onto the material sample. The other measure is known as the extensometer, which is already shown here, that measures the stretch or detects the amount of elongation, the increase in the length of the material sample because of the applied force. So in that case, the machine is gonna keep on stretching the material, and it's gonna keep measuring the force, detecting the force through the force sensor. And in the meanwhile, it's gonna keep on measuring the stretch of the material that is going to be generated for every single force that the machine applies into the material sample. And the machine is gonna keep doing so till the material sample will be completely fractured. Then we're gonna drive a figure. From this figure, which is known as the force displacement or force elongation curve, from this curve or figure, we are going to extract so many of the mechanical properties of the material as it will be shown to you. Make sense? So simply during the tensile test, the specimen or the material sample is deformed till fracture, to be completely fractured with a gradually increasing tensile load or tensile force. So the machine, as I mentioned, is gonna keep on increasing the force steadily, step by step. And the new displacement or the new elongation for every increase in the force, it will be recorded. It will be determined through the extensometer that is already fixed over the material sample. In that case, we can determine exactly the relation between the force and the elongation. From this relation, we can drive so many mechanical properties. The load is applied uniaxial. So this is known as uniaxial stress or uniaxial applied load along the longitudinal axis or direction of the material sample, in the longitudinal direction of the material sample. Like you already gonna keep on stretching this material sample in both sides. Make sense? So I'm just gonna let you with this video that explain in detail how we are running the tensile test for two different material samples. One is with a yield point phenomena and the other one without yield point phenomena. And it's gonna be explained through the video what does it mean yield point phenomena or without yield point phenomena. Make sense?
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts, and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Ludus Effect. After a certain strain, known as the Ludus strain, the force increases again. The material opposes an increasing force against the imposed elongation. Its strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. initial linear curve in the force elongation diagram again shows the elastic behavior of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behavior to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material.
As explained in the video, the test is done in this way, like it is carried out in this form. Like we start with a material sample with a gauge length L0 or an original length L0 and original diameter D0. And then we are going, so this is the material before stretching, before doing any stretch to the material sample. Then we are going to apply a force over the material sample. Then upon this force, the material will be elongated. And we can refer to this elongation, which can be simply calculated as the difference between the new length of the material negative the original length. This is going to give us delta L. So we can simply define the elongation into the material sample by delta L. This delta L can simply be represented as the new length negative the original length of this material sample. So for example, if we started and the machine start to draw a curve, as already represented in the video, between the elongation, which is delta L, versus the force versus the elongation. So this is the force, this is the elongation. Initially, we have nothing in terms of force, so definitely we don't have any elongation. But upon increasing the force, there is an elongation that is start to show up. So the machine, it works in this way, like it applies a force, then it measures the corresponding value of elongation because of that force. And every force is responsible for a certain delta L within this material sample. In order to stretch the material more, we have to keep on increasing the force. So we have to increase the force. So as the force increases, so if we draw the relation between the force and the elongation, the force is going to keep on increasing and correspondingly the elongation is going to increase. And simply how we can calculate the elongation is going to be the instantaneous length. So we can add here a subscript I, stands for like the length at for the force Fi, like for every force, like F1, we can have L1. For F2, another force, we can have L2 and so on. So this I is going to be counted as the instantaneous length that is corresponding to a certain applied force acting on the material. If we subtracted the original length from the instantaneous length, we're gonna end up with the instantaneous elongation into the material, with the elongation at this instant of time, with the elongation that corresponds to a certain force Fi. As we keep on increasing the Fi, or increasing this force, definitely the elongation is going to be increased. Make sense? So initially, the material, it works elongated in its elastic behavior within the elastic region. What does it mean this? It means that, for example, if we're going to keep on increasing the force, the elongation will keep on increasing linearly in relation to the force. It means that the relation between the force and the elongation within the material is going to be a linear relation. It's going to be shown as a straight line, a linear line, as a line within the force elongation diagram or curve. Make sense? Within the elastic behavior of the material, for some reason, if we stop the test or we remove the force, so the material can restore back again to its original dimension. It means that it works in that case, the material works like a spring or works like a string. Like you're gonna stretch the spring. Once you remove your hand, the spring will return to its original dimension one more time. So the material within the elastic behavior, it behaves like it is a spring. Like assume that you're already holding a spring from two opposite sides and you fixing one side and you stretching the material with a force F from the other side. So what should be happening to this spring? The spring will be elongated, typically the same way like the material sample. Then once you remove your hand, once you remove the force, cancel the force, the spring will restore back again to its original length. And this is typically what should be happening to the material as long as the material is still in its elastic region. So for example, for some reason, if we remove the force at this instant of time, we're gonna keep applying a force, increasing the force, increasing the elongation. At this instant, if we decided to stop the test, or we remove the force, the material will restore back again to its original dimension. It will restore back again to the original shape and dimension, to the zero case. But if we're gonna keep on increasing the force, the material to a certain limit, beyond a certain limit value, so we're gonna keep till it will move to the yield region or the yield point of the material. Some material, as already shown in the video, the first material sample, which was steel, the steel is gonna show like a abrupt change or a sudden drop in the force within a region. Then the force is gonna be like almost constant, then it's gonna move to another like a curve. So this region is known as the yield region or the yield point of the material. This is the transition point between the elastic behavior of the material and the plastic behavior of the material. If we gonna keep increasing the force and we enforce the material to move to the plastic behavior or the plastic region, in that case, for example, let us assume that we gonna keep on increasing the force, we reach the yield, we gonna keep increasing the force till we reach up to this point. Now if we decided to stop the tensile test or to remove the force, the material will not be able to reset back again one more time following the same curve to reset back again to the original dimension. No, the material will show a permanent change in the shape and the dimension, indicating that the material has been moved to the plastic behavior. So this is what distinguishes the elastic behavior of the material from its plastic behavior. What distinguishes is that within the elastic region or the elastic behavior of the material or the elastic limit of the material can restore back again to its original dimensions and shape upon the removal of the force. But in the plastic region or the plastic behavior of the material, if we try to remove the force, the material cannot restore back again to its original shape and dimension, and instead the material will show a permanent change in the shape and the dimension, which cannot be restored back again one more time. And in that case, if we removed, now we are in the plastic region. If we remove the force, the material cannot restore back, and instead the material will return parallel to the elastic line. This is the elastic line or the elastic region line. This line is gonna move parallel to it, showing a permanent elongation. This elongation will be formed into the material and it will not be restored back one more time unless we melt the material completely and we start to reshape the material one more time, for example, or do other things over the material. But in that case, we're gonna have a permanent delta L, permanent elongation of the material that cannot be restored. Why? Because we have moved to the plastic behavior. So within the plastic behavior, the material will start to deform permanently. It means that there is no ability to restore this permanent change one more time within the plastic behavior. And again, what distinguishes within the curve the elastic from the plastic behavior is the yield region. This is known as the yield point or the yield region of this material. In some materials, as I already explained in the first video or the first test, like the steel, it has its yield region. It is clearly can be seen in the curve. Like this material is known as a material with yield point phenomena, and in that case, we can clearly see the yield point that distinguishes the elastic from the plastic region. But in some other material, like the aluminum alloy, in the second test, they tested aluminum alloy. In the aluminum alloy, it shows a smooth transition from the elastic to the plastic. It means that the yield point, it is not clearly seen. There is no specific yield point, and in that case, this material will be qualified or named as a material without yield point phenomena. But the yield behavior is still there. It is not clearly seen in the curve, yes, but it is still there that distinguish the elastic from the plastic behavior of the material. And I'm going to show you how we can determine this yield behavior or this yield point or region for both material without yield buoyant phenomena or with yield buoyant phenomena. Then also during the video, there was a nicking. So before the nicking is shown into the material sample, the material will work based on strain hardening. What does it mean, strain hardening? And this is what we are going to explain with more detail over the next chapters. Strain hardening, it means you could understand it like that the material still resists the applied force. The material has the ability to resist the applied force. It means that in order to stretch the material more, we have to keep on increasing the force. And this is what is typically happening within this region. Like for example, if we're going to consider this region beyond the yield point, the material behaves according to its strain hardening ability. Like for example, starting from this point, in order to stretch the material more, we have to keep on increasing the force. So the forces keep on increasing till the necking point. The necking point, the force that corresponds to this necking point or the formation of the neck, the initiation of forming the neck, takes place at the maximum force when the material reaches its maximum ability. At this maximum force, the material becomes very weak and the neck will start to form and the material will start to be ready to be fractured. And in that case, the material can be easily elongated even with a lower level of forces without any need to increase the force more beyond the necking point. In that case, as we keep applying any force over the material will likely to be able to be fractured because the necking will be keep on forming and increasing till the material will be completely split or fractured at this point. So this point is known as the fracture point of the material. So this is the procedure, how the material is going to deform upon an increase in the force till it will be completely fractured during the tensile test. From this curve, we can derive so many mechanical properties of the material. One of the things, for example, that we were able to identify the yield point or the yield region that distinguish the elastic behavior or the elastic properties of the material from the plastic properties of the material. In addition to this, we can derive so many other mechanical properties. So, as already explained in the video, this is a representation. What is the difference between a material without yield buoyant phenomena or a material with yield buoyant phenomena? This material is a material without yield point phenomena. Why without? Because as you can see, this is the straight line. This is the linear relation between the force and the elongation or the stress and the strain. So before I explain this to you, something that you should understand that the machine gives us force versus elongation. Then simply we can convert this force elongation curve into a stress strain curve. How we can do so? Simply, if you divided every single force, because in the machine there is a sensor that detects the force, right? So it means that we're gonna end up with like a table. So many values of forces, and these are the corresponding values of the elongation. Next to every force there is elongation. For every force there is a certain amount of elongation. So if we divided every single force over the original cross-sectional area of the material sample, as you can see in this sample, it is cylindrical. It has a cylindrical shape. It means that its cross-sectional area is circular. And the area of any circle that we knew this from even the high school with a diameter d, so this is the original diameter d0 of the material sample, we can calculate the original cross-sectional area of this material. The cross-sectional area, it will be pi over 4 the diameter square. The area of a circle in terms of the diameter, it is pi over 4 diameter square. But in terms of the radius, it is pi r square in terms of the radius. But since the diameter in many of the cases is the thing that it can be easily measured using the some measuring tools, in that case we can determine the diameter, and in that case we can determine the cross-sectional area as pi over 4 d0 square. Make sense? So simply, if you divided every single force by the original area of this material sample, we can convert this force into stress according to this relation. As we said, during the tensile test, the material is subjected to a tensile stress. How much is this tensile stress? It will be the force divided by the area. But here remember that we are dividing by the original area of the material sample. That in that case, we're gonna end up with stress. So we can convert this vertical line into, or axis into stress, which it can be counted as the force divided by the original area. How about the elongation? It can be converted into strain. And from the mechanics of material, especially for mechanical engineering, you should understand the difference between stress and restraint. The strain, which we can refer to it as epsilon, is going to be the delta L divided by L0. If you divided every single elongation, as I said, there is a table. There are lots of forces and there are lots of corresponding values of elongation. For every force, there is elongation. For every force, there is elongation. So if you divided every single elongation by the original length, L0 of the material sample, in that case, you're going to end up with strain. And in that case, we can convert this axis, we can scale it into another scale, which is known as the strain. And in that case, we're going to end up with the stress-strain curve. The stress-strain curve is going to be almost having the same shape as the force-elongation curve, but different scale. Because here we are dividing over E0, here we are dividing over L0, in that case, which is delta L over L0, in that case, we're going to end up with a similar shape, but different dimensions. Make sense? And from the stress-strain curve, we can drive the same mechanical property that we can drive also from the force-elongation curve, but it is commonly used. The commonly used curve is the stress-strain curve. Now the tensile testing machine, since it is already connected to a computer, the computer can do this calculation. The computer can do the calculation and the division of the force over the original area and the elongation over the original length to end up to give you directly, to print to you directly the stress versus the strain at once. The other option is that you're gonna print or extract the force elongation curve, and in that case you're gonna do this division by yourself. You're gonna divide by the area, divide by the length to convert this curve into stress-strain curve. Make sense? So as I said, here we are comparing between the material with yield point phenomena without yield point phenomena. So this is a material without yield point phenomena. A typical example of this material is aluminum. As already shown in the video, when the tensile testing machine gave us the curve with a smooth transition from the elastic behavior to the plastic behavior. There is a proportional limit. This is proportionality limit, which is referred here as point P. This point indicates this is the end of the straight line. Beyond this straight line, a curve will start to form in relation between the force and the elongation, or the stress and the strain. And here we have a smooth transition, as I mentioned, from the elastic to the plastic behavior of the material. So the question is, where is the yield point, or where is the yield region that distinguishes the elastic from the plastic? Definitely, as already shown here, we can count that once the material finishes its proportional or its linear relation, this on the left of this, from this point, this will be counted as elastic behavior of the material. Beyond that point, this will be counted as plastic deformation of the material. The same thing here for the other type of material, which is material with the yield point phenomena. A typical example of this is the steel. When we tested the steel as shown in the video, we end up with like a sudden drop or a decrease in the force in relation to the elongation, and we're gonna have this like unusual behavior of the material. This indicates the yield region or the yield point of the material, and the amount of stress that is corresponding to this value, by the way, is known as the yield strength or the yield stress of the material, and this is something that we are going to discuss. But at the end of the linear relation, there is the proportional limit. So this is P that distinguishes the elastic from the plastic behavior of the material. At that point, if we draw like a vertical line, we can simply split this curve into the elastic region on the left and the plastic region on the right. It means that beyond that point, the material will not be able to restore its original shape one more time, and instead it will show a permanent change in the material shape and dimensions. and then the material will start to move to the plastic behavior as we mentioned before. So this is the elastic, this is the plastic behavior of the material, and as you can see, this region can be clearly seen. We can easily identify what is the yield point, and at this point or at this value of the stress, the amount of stress here is known as the yield stress, and the corresponding yield stress is known as the yield strength of the material, which is a material property. What does it mean, material property? It means that it distinguishes one material kind from another material. So for example, the yield strength for steel definitely is different than aluminum, is different than copper, is different than magnesium, and so on. So it is a material property that is different from one material to the other. One of these material properties that we can identify using the simple tensile test is the yield strength of the material, or the yield stress of the material, that we can refer to it as sigma y, which stands for the yield strength of the material, or we can simply call this one as the yield stress, because in a way it is a stress of the material. So from this we can understand that the strength, it is measured by the amount of stress that the material that can withstand without moving to the plastic deformation. So again, the yield strength of the material, it can be measured by the maximum stress that the material can withstand before going to the plastic behavior, before showing any plastic behavior of the material, or the maximum stress that the material can withstand within its elastic behavior that needed to keep the material within its elastic behavior. This also could be counted as the yield strength or the yield stress of the material. So for example, the engineering utilization or using materials, when we as engineer using a material in building a bridge as civil engineer, or building a machine like mechanical engineer, or building whatever, in that case, in many of the cases, we have to operate this material or use this material at stress levels lower than its yield strength. Other than that, the material will be, or our design of the material will be counted as a failure, because the material will be moved to the plastic behavior. In some other engineering application, we would need to move the material to the plastic behavior. Other than that, we're gonna count this design of this process will be counted as failure. Make sense? All right, so for a material with a yield point phenomena, we can clearly see and identify what is the yield strength. We can identify from this curve, clearly we can allocate what is the yield strength of this material, no problem. But how about a material without yield point phenomena? Without yield point phenomena, we do have a smooth transition from linear to non-linear, from elastic to the plastic behavior. So where is exactly the yield strength of the material? It is based, this is a standard thing, and this is what is common for most of metals that already behaving in this form, like aluminum and like any metal without yield point phenomena. It is commonly accepted and agreed in the scientific community that for guys who are working as over material engineering or material science, that in order to determine the yield strength is gonna be at the 0.002 of a strain of the material. Like for example, what we basically do, this is equivalent to the 0.2% of the original length of the material. 0.2% of the elongation of the material. We can simply, of the length, of the original length of the material, we can identify the strain value, which is 0.002. And then if you draw a line that is parallel to the elastic region, this line is going to intersect with the curve, with the nonlinear curve of the stress-strain relation at a point. And if you mark this point and draw another horizontal line to intersect with the vertical axis, you're gonna allocate the amount of the yield strength or yield stress of the material. So this is commonly fixed. Now that for most of metals, behaving in this way without yield point phenomena, how we can identify their yield point or yield, not yield point, to identify their yield strength or stress? In that case, you would need to measure over the strain axis 0.2% of the original length of the material sample, which is gonna be corresponding to 0.002 strain, You're just gonna measure 0.002 strain. Then you're gonna draw a line that is parallel to the original linear line. It should be completely parallel. It's going to intersect at a point with the curve within the plastic region. From that point, if you draw a line horizontal to intersect with the vertical axis, the corresponding value of the stress, this will be counted or considered as the yield strength or yield stress of the material. Make sense? So, as we explained, there are lots of mechanical properties that we can derive from these curves. Some of these mechanical properties is the yield strengths, which distinguish one material from another material. And I showed you here how we can identify this yield strength for a material without yield point phenomena or with yield point phenomena. It can be clearly identified or seen in the material with the yield point phenomena. For the case of material without yield point phenomena, we have to draw this line. So, what is an elastic behavior? We already explained this. Elastic behavior, as we mentioned, in the elastic region, when removing the external tensile force or tensile stress, the material can restore back its original shape and dimension one more time. This indicates that the material works like a spring and the material behaves elastically. It means that it works within the elastic behavior. In the elastic region, the stress varies linearly with the strain, and this dominated by a law which is commonly known as Hooke's law. So Hooke's law, it is only applicable within the elastic behavior of the material, that the stress is linearly related to the strain. There is a linear relation. This is a line that it should be seen in the stress strain curve. The slope of this line is known as E, which is known as the Young's modulus or the elastic modulus or the modulus of elasticity. And again, this is another material property that distinguish one material from another material. So what does it mean? It means that aluminum has its own elastic modulus that is different than copper, that is different than steel, than iron, and so on. So it is a material property. For every single material, there is a specific value for the Young's modulus that distinguish one material from the other. Make sense? So how we can determine this E or this elastic modulus, simply it can be measured at the slope of the stress-strain relation within the elastic region. So for example, if you just measure the slope of this line, this slope, it should be angled, there should be an angle. If you form a triangle and you measure this angle or determine this angle from the curve and the tangent of this angle, this definitely is going to give you E, which is the elastic modulus of this material. Make sense? Within the plastic behavior, this is another behavior, another thing of the material. Within the plastic behavior or the plastic region, a plastic strain, which will be counted as a permanent material deformation. It means that the material will change its shape permanently. It means that we will not be able to restore the original shape one more time, as I mentioned, is produced due to the applied force, as long as the material moves in the plastic behavior. As we said, within the elastic, the material can return back one more time, but if we exceeded the yield region and we move to the plastic behavior of the material, and for example, if we stop the force or increasing the force at this point and we remove the applied load, the material cannot restore back again. And instead, it will be moved parallel to the original length. So we reach it up to this point, we have reached a certain amount of strain, as long as the force is still there. So what is happening? That we are keep on increasing the force or keep on increasing the stress, and the corresponding strain is gonna keep on increasing up to this point that is correspond to this stress. But for some reason, if we decided to stop the stress, to remove the stress, the material will restore back again in that way. It means that there will be kind of a spring back. So the difference between the total strain at the instant that the force is still applied, once we remove the force, the material will spring back. So this is known as a spring back behavior of the material, and this depends on the stored elasticity or restored elastic energy within the material. This is known as the spring back of the material. To understand the concept of the spring back, let us consider the simple example of a stick that is made of metal. Assume that I give you a rod or a stick that is made of metal, very thin stick. Then I ask you to bend it, but try to bend it with a very slight force in the beginning. So if you apply a very small force over this stick, it will be bended, yes, but the bending it is not that much. So in such a way, if you remove your hand, it will spring back again. It will restore back again to the original straight position. Initially, this stick is perfectly straight. If you apply a small force, it will be slightly bended. But once you remove your hand, it will restore back again to the original length or the original shape, straight shape. But how about if you repeated the test, but in this case, I ask you to apply a very high force on it. In such a way, it will be highly bended. So it completely bended, but once you remove your hand, you're gonna find that the stick, it will be spring back slightly, it will be open slightly, but it won't gonna be able to be completely straight one more time. Why? It had moved to the plastic behavior, so there is no ability for the material to restore the original shape. It has been bended. Originally it was straight, now it has been bended in this way, so we don't have a permanent change in the shape. The shape is different. This is a shape that is different than this shape. Because of the applied force, it is highly bended. But the instant that you remove your one hand, the one side of this rod or stick, it will be opened, somehow slightly open, indicating the spring back behavior of the material. But it will not be completely open, and instead it's gonna have a plastic strain. This region, this amount of strain that we can measure from that curve is gonna be considered or counted as permanent deformation or permanent change in the shape over the original shape of the material. So this is a typical example. What does it mean as spring back, which depends on the elasticity that is stored within the material and the plastic strain or the permanent change in the shape of the material within the plastic behavior. In the plastic region, the material cannot restore its original dimensions when or shape or removing the external applied force, and in that case there is no linear relation anymore between the stress and the strain. Within the elastic region, the stress has a linear relation with the strain. There is linear stress-strain relation that depend on and the slope of this relation is known as the elastic modulus of the material. But within the elastic region, we most likely gonna end up with a bar law. This bar law that relates the stress to the strain, and this K and N, these are known as the strength constant, and this N is known as the strain hardening exponent. These are the two material properties that we can even drive them by investigating the nonlinear curve within the plastic region if we are interested in finding how much is K and N for a certain material. So these also are two other material properties that we can drive from this stress-strain curve. Make sense? But remember, within the plastic behavior, there is no linear relation anymore between the stress and the strain, and instead we're going to end up with a non-linear relation.